Okay, so we will continue. So before we go ahead, I think we can compare dynamic programming with RL. So in RL literature, they use environment, and then we use systems here. In the DP terminology, we have agents there, and here we call it control or decisions. We have actions there. Here we have decision or control. An agent is the decision maker or controller, and then reward is used in RL, but here we use cost. And then we have state values, which is typically like the opposite of what we use here. So here it's more like a cost. There again, state value would be the intermediate reward there, and value or the reward function here. So as I said already, maximizing the value function here, it's minimizing the cost function. Action value is called Q factor here, and planning means solving a DP with a known mathematical model. And learning is used in RL literature, so here we call it solving a DP without using explicit mathematical model. So basically you learn it from the data that you generate. So self-learning, here it will be solving a DP problem using some form of policy iterations. Deep reinforcement learning, here we call it approximate DP using value or policy approximation with the deep neural network. Prediction is policy evaluation. Generalized policy iteration is optimistic policy iterations. State abstraction in RL, here it means state aggregation. So aggregation is something we will see in more detail. Temporal abstraction also, here it means time aggregation. Bellman operator is a DP operator, and so on. Experience replay in RL, here it means basically reuse samples that you generated while you doing the simulations. So some of these we will see in more detail as we go along. So we will look into more today. We will look into more detail in the sense that we will formulate the problem as a general discrete optimization problem. We can keep it deterministic right now, and discrete and finite horizon. So within this, we will see a few other examples today, and obviously the approximations that we will do will be mostly rollout types, and then we will see more. There are quite a few examples, so let us see. So let us recall DP with finite horizon. So that's something we have already we have defined this already. So here we have like finite number of time horizon n, and it's deterministic, so we don't have any disturbance term W here. So we have seen this before. We are just recalling these things. So we have state space xk control uk, and fk and gk are as before, and this is our cost in the deterministic case, and this is the optimal cost. So obviously in DP we optimize over the sequence of controls, and we use the word policy also. As you have seen, we started with controls, but then we introduced something called policies. Policies are given by mu. So these policies, mu k maps xk into controls uk, and the whole point of introducing policy was to help in the stochastic case, basically. Okay, so basically where controls are not necessarily fixed. So even if you, let's say, determine a policy, then the controls are kind of fixed. So u0, u1 up to un, you use these when the controls are kind of determined, but then in the stochastic case, you allow some variations in the control. So that way you use policy. So that's what I said. Policies allow changing control dynamically in the presence of uncertainty. So that's why we use the term policy when you are in the uncertain regime. Okay, so all this is something we have done, and so this is the DP algorithm. If you can recall, it starts from the terminal cost, and then it computes the kth step cost, and so this is the optimal one. So that's why we have a star here, and finally we get the final cost. And then after that we get the controls. So controls are the ones that minimize the cost. So this way we generate all these controls u. So all this is something we have done before, and in deterministic finite horizon problems could be written as a graph with the initial states and then the terminal state, and then you take certain controls and you go to the different states and so on. So all this is something we are revising again. So this is So in a deterministic finite horizon case, it could be written as a graph. So that's the main takeaway, that we can write this as a graph with some initial states, and we terminate at the so almost all problems, in fact it's equivalent. So any finite horizon DP problem is equivalent to this shortest path problem. So whenever you encounter a finite horizon problem deterministic, then you should write down maybe the in terms of graph like here, and shortest path is basically minimizing the cost. So this is something we keep in mind. So that's what we say here. A deterministic finite horizon problem is equivalent to finding a minimum length shortest path problem. So from modeling perspective, whenever you encounter such problems, you always write down as a shortest path problem. Okay, so this will clarify the types of problem you want to solve. So whenever it's in this regime, always write down as shortest path problem. As we know, many problems will fall into this. So as an additional example, we will look into this 4 queens problem, and does it go in that framework of shortest path problem.
The n-queen problem.
In 1848, German mathematician Max Bizel came up with a problem that combined puzzles with his favorite game, chess. He asked how many ways it was possible to place 8 queens on a chessboard so they don't attack each other. Without computers, the solution took a couple of years. But new technology has raised the record for the answer up to boards of size 27. Specialized FPGA hardware was used to find the 234 quadrillion configurations. Among games, chess stands out in AI history. In 1950, the great Claude Shannon predicted many of the essentials for automating good play. Within 50 years, computers could beat even the best of human players. Placing queens on a board is an example of the more general AI challenge of constraint satisfaction problems, or CSPs. To look at the basic techniques, we'll use a mini 4x4 board. The most basic approach is to place the first queen on any empty square, so 16 possible positions. We can then add the second queen, giving 15 new branches each time, for a total of 16 times 15 nodes. At the next level, there are 14 empty squares left to choose from, and for the final queen, 13 choices. 43,000 final nodes is a large number, and we can do much better. We can use the structure of the problem. When you place a queen, no other queen can go in the same column. You can say the same about the rows, but we are going to use the columns. So let's use standard chess A, B, C, and D for the columns, and number the rows conventionally from the bottom. Now when you look at the queens one at a time, there are 4 basic choices for A, 4 again for B, and for C and for D. Since the order of placing the queens doesn't matter, we only have to consider one of A, B, C, or D at each node. We've cut the number of leaf nodes in the search to 256.
Can we do better?
So let us see that. So 4 queens problem is a problem where you have 4x4 portion of a chessboard. So this is a 4x4 grid, you can see. And queen, you know, in a chess board, how the queen can move. So there's basically the queen can move any extent horizontally on either directions, or any extent vertically, and also any extent diagonally. Okay, so these are the moves allowed for a queen.
The king might be the most important piece in chess, but the queen is by far the most powerful. Like the king, the queen can move in any direction, forward, backward, to the sides, as well as diagonally. Unlike the king, the queen can move as far as she wants in any direction. The one thing the queen can't do is jump over other pieces. Let's look at some queen moves. In this position, the queen could go all the way up the diagonal. She could slide all the way across the board. She could now move all the way down here. Or she could make some shorter moves, like here, here, and here's another queen move.
So the 4 queens problem is a problem where you are supposed to put one queen per row and per column. So there should be only one queen per row and per column, and such that they don't kill each other. Okay, so that's the 4-queen problem. So in this case, in this example, you can see in this framework, this is a 4x4 chessboard, and here are these queens safe, right? So you put here, let's say, first queen here, and of course first queen has no danger, so first queen just sits there. Let's say we put a second queen there. So if we put a second queen here, so then this is the second queen, and then this has any danger? No, not really. So it cannot be killed by any of the existing ones. And then in the third step, you put another queen, and is this queen under danger? No, it cannot be killed by anyone else, so that you're safe. And then the fourth queen you can put here, and this cannot be killed as well. So in this game, if you arrive at this state where the 4 queens are there and they cannot be killed by each other, then we say that the problem is solved. Okay. So same way here, you can have various ways to arrive at the same answer. So in this case, if you see, this is also a valued solution to this problem. So now this is a sequential decision making problem in the sense that I can do it one by one. So I want to, rather than thinking of putting the 4 queens simultaneously on the board, I want to do it step by step. So in the first step, I say that let me put the first queen here at the k equals to 1, and then the second queen at k equals to 2, and see if the second queen is safe or not. And then I put k equals to 3, and then I check whether this queen is safe or not. And then I for k equal to 4th time step, I check whether this queen is safe or not. So so this 4 queens problem could be seen as a simultaneous, let's say you put all possible 4 combinations of these queens, and then kind of it's a rearrangement problem, like you want to put 4 pieces on 4x4 grid, so the space will be quite huge, and then you may want to play around with that. But then here we want to see this as a sequential decision making problem where we want to go from 1, 2, 3, 4. Okay, so so this is the 4 queens problem. So 4 queens must be placed on 4x4 portion of the chessboard so that no queen can attack another. In other words, the placement must be such that every row or column or diagonal of the 4x4 board contains at most 1 queen, because the queen, if you put on the diagonal, obviously they will kill each other. So here we see this problem as a sequence of problems. First placing a queen in the first 2 squares in the top row, then placing another queen in the second row so that it's not attacked by the first, and similarly placing the third and the fourth queens. Okay, so it's sufficient to consider. Also, we should note that due to the symmetry of the problem, it is enough to focus, let us say for the first queen, it is enough to focus only on these 2, because these ones are symmetric. These ones are symmetric. So putting something here or here is symmetric. Putting something in the second one is the same. There is a symmetry there. So it is enough that you consider only the first 2 squares of the top row. Okay, so here by first 2 squares of the first row, it means that you only focus on, let's say this and this only. Okay, because due to symmetry, because these are by symmetry, these are kind of equivalent. Okay, so this is the 4 queens problem, where you are supposed to solve your problem, where you get the maximum reward when you arrive at. So here what you see here is indeed the solution to the problem. So this is our solution 1, this is our solution 2. So either way, if you arrive at one of these value terminal state, then you are given very high reward. So since this is a problem where we want to see that many puzzles or games also follow deterministic finite horizon model. So how do you write them as a graph with nodes and vertices? So we know that any deterministic finite horizon problem can be written as a graph problem with states represented by the nodes of the graph, and the edges are the cost, which could be seen as the edge length, or the edge weight are the cost. And your goal is to go from it's a shortest path problem. You go from start to the terminal state. Okay, so any DP finite horizon problem you should be able to write that. Now the whole point is, which are those problems? So this is one of the problems where we are saying, look, some of the puzzles could be written as this in a graph way. So we have a starting node S, and then we look into possibilities here. So here our initial configuration is like there are no queens, so that's our starting state, and then we say what are the possible actions or decisions or controls that I'm going to take. So as we have seen before that it only for the first row only the first 2 positions, left positions of the first row matter. So basically these 2 matter. So basically it's all about where the queen will go in the first row. So there are 2 possibilities there. So we put first possibility is this one, and the second possibility is this one. So these are the 2 possible states from there, or the 2 possible actions that we will take, and then that will lead us to 2 possible states. And then from here, the question is, where should I put the second queen? So if I put the second queen, let's say here, then this is one possibility, and then obviously we cannot put in the second step. We cannot put it here because this is you will be killed by the queen. You won't be able to put it here. So then you are left with these two. So let us say we put it in the one where we circle in red. And another possibility. So another possibility is that you put this here, which is indicated here, and so these are the two possibilities that come from this state. And then we explore this state. So in this state, where we see that what are the possibilities. So we saw that we could put this here, whereas we could not put anywhere else because if we see here, then this we cannot put here, this we cannot put here, this we cannot put here. So basically these were the only possibility. And then now out of these three possible states, now we look at where we will put the third queen. So if we put the third queen, let us look into the first state here. Can we put the third queen anywhere else? So if we see here, then what we find is that we cannot put the queen here. We cannot put the third queen here. We cannot, because this will be killed by this, and this will be killed by this. We cannot put the queen here because this will be killed by this, and we cannot also put it here because this will be killed by this. So basically we have arrived at something called dead end position. So this is the end. And we will from here there is nothing to do, so you will go to the terminal state. Now let us look into this state, the second option, which is this one. Now we can think whether should I put the queen here. No, I cannot put it here. Can I put it here? So this looks okay. Can I put it here? No, because this will be killed by this. I cannot put it here as well. So this is what is done here. So this queen is here. Okay, so this is one valid possibility. And then we look into this this one again. So here, what are the possibilities we have? So can I put here? So it looks fine. Here I cannot put. Here I cannot put. Here I cannot put. So as you can see here, so we did put a queen here. So these were the two possibilities, remaining possibilities. And from here we see how we can solve our problem further. So then we do as we have done before. So can I put a queen here? No. Here no. Here no, here no. So this is kind of a dead end position, so that stays there. And then if we look here, then we see, can I put here? No, no. But here it seems like I can put a queen here, but here we cannot. So that's pretty much the final state where we are successful in putting 4 queens in a 4x4 chess grid. So that they don't kill each other, and this is a valid solution to this problem. So as you can see, there will be many puzzles like that, and you should be able to kind of treat this as a sequential decision making problem, where you start from one state and then you sequentially think what are the actions that you are supposed to do and what are the possibilities to reach the terminal state. Now to model a problem like this, you can say that the edge weights are 0. So whenever you go to the edge weights, these are 0, 0, 0. As long as you are going successfully and arriving at the end stage, then your cost is 0. Whereas if you arrive at dead end, then from dead end while going to the terminal, you give a cost of 1 and give a cost of 1. Now the question is, why should I think in that way? Because so the idea here is that as long as you can move forward, there is 0 cost because you are going towards the solution, which is like 4 queens on a 4x4 grid. But in case you hit a dead end, then you give a high cost of 1. This means that route is not supposed to be taken. So the policy should update such that, so overall the cost, if I see the cost of going via this route, this is a dead end route, the cost is 1. And then if I see this route, then the cost is 1 as well. Whereas if we go via this route, then the cost remains 0. So as we see many types of puzzles and all this, you may have to do this initial modeling part, how you model your problem, and then once you are there, then you can apply the RL framework and do all kind of rollouts and so on. So so as I have said before, in this small problem we have seen in 4x4 queens problem, we could solve the problem easily. In fact, we solved it just now. But then for a very large n, for very large large chess grid n by n queens problem, you can see that these branches will explode a lot. Okay, so kind of there will be exponential increase. For example, for n equals to 8, there will be 8 to the power 8, or more than 60 million possibilities. So that's when you will go for approximate approaches, approximate value function approach, and then you will do the rollouts and do the improvements on that. Okay, so So this is something you can explore as an exercise for the n by n queens problem. And so you will see this in one of the assignments where you will apply approximate DP to solve this problem. Okay, so I gave you the modeling part. Now you can do the coding to improve this. We can, in the deterministic finite horizon case, we can write down a general discrete optimization framework, which could be written just like this. So overall, it's an optimization method. So which means that I'm supposed to minimize a cost function GU, and G is a function of control. Now this is in the deterministic finite horizon case. What we observe is that what is decided, what decides the next state are nothing but control. Okay, so state remains a hypothetical step. But if I can think everything as control, okay, I reach somewhere, but then overall, if I throw away kind of the states and all, what I really know is like I have to take a couple of sequence of controls. So overall, it's a function of control, and I'm minimizing over that. So it is possible that I may throw away the states and I just write control. So my first state is control U0. My second state is control U0, U1. So this sequence defines a state for me. Okay, so it's possible. So this is what I mean. I can throw away the states. So then U0, U1, U2 is my state 3. So this acts like state 0, this acts like state 1, this acts like state 3, and so on. Okay, so that's what it's all this is trying to say here. Okay, so basically this is what I mean, that overall we can just look at a sequence of controls as states. So this is nothing like nothing much here. Okay, and we can also do approximations and so on. Okay, so all this is what I said, and then this is just the same thing, like rewriting the cost when your states are written like sequence of control. So basically what we know before is that this was supposed to be our xk minus 1, and then we have written xk minus 1 as a sequence of u0 to uk minus 1, and so basically this is a minimization over these. So basically these are just the notations with this new notations. So this is our state xk minus 1, and we are looking for a control uk. Okay, so and then we can do the approximations in these and so on. So this is just a notation thing. Okay, so now here one of the thing is like, can I solve a feasibility problem? Like sometimes you may encounter a problem where you are supposed to solve problems like this, where someone is asking you, look, I have a function hk, and then I want to see whether it satisfies the constraint uk plus 1 is less than equal to 0, and uk comes from some control. Okay, so this is a feasibility problem. We call it feasibility problem. So here we can rewrite this as an optimization problem where it's about minimizing this cost. Okay, so this is like minimizing this. So if you encounter a problem like this, where you are supposed to satisfy the feasibility as you go along, maybe it's a robot and it is supposed to be constrained along certain path and so on. Let's say hypothetical example. So so here you are supposed to satisfy certain constraints, and that itself is a DP problem. Now if you can notice this objective, the trick here used is max of 0 HKXK. So if you see that the way these costs are written is that whenever you are going to choose these UK, it should be such that it does not exceed the 0, okay, which is what is given by this constraint. Okay, this is kind of equivalent to kind of minimizing this. Okay. So any feasibility problem, you may use a DP to solve problems like that. Okay, with this trick of max of 0 and this. Okay. And this is again a recall. This is nothing new right now. We can do approximations in the value space and so on. So I will just go over this. We can write a Q factor and then do an approximation with respect to the Q factor. Again, I will skip this. This is okay. Let us go to the to further topics. So and yeah, so we are aware of the rollouts. In rollouts we have like heuristic greedy policies, and based on that we kind of improve on that. So rollouts could be written from k+1 onwards as applying some heuristics after that. So rollout could be usually seen like this, that you kind of minimize the local cost UK, and then from k+1 onwards there is a heuristic that will give you a cost estimate. Okay, and then you can also write this in terms of Q factor and so on. Okay, so this is the same thing. So this is what we do in basically in rollouts, that at XK we explore various controls, and then out of these explorations we apply the heuristics and calculate the total cost, and out of these whichever was the minimum, we update our policy. So in this case, let us say if this gave us overall the minimum cost, then we update our policy for XK. So all this is kind of a repeating thing. So now let us do an example again to refresh ourselves from of how these rollouts could be done. And this will be, you can think of these as again in the multi-agent framework, because there will be two agents trying to improve their policy using rollout. Okay, so this is a multi-vehicle routing problem where there are multiple vehicles. So in this case, there will be two vehicles, and it's a routing problem, planning problem. So if you are working in a let us say planning, because there are quite a few startups I have seen. I have also met some of these guys. So they in some conference, so their whole idea is to do this this multi-routing, the routing of the trucks and so on. Okay, so and this is a big
vehicle routing problem.
You must handle hundreds, even thousands of delivery points every day. Say your fleet has 100 trucks. Then you have to draw up a delivery plan for 100 trucks, 1,000 locations every day. Your plan must minimize cost and at the same time maximize efficiency. How do you manage that? This is exactly the question of Vehicles Routing Problem, or VRP. This is one of the most difficult math problems to solve, when you have to consider multiple constraints, like the number of vehicles, vehicles capacity, time window of stores, types of goods, number of depots, split deliveries, human resources, traffic, and road condition. However difficult it is, solving this problem can be super beneficial to you and your organization. When you solve VRP, you can improve vehicles utilization, meaning you can transport more goods in one go. Consequently, your fleet's traveling time will be reduced, so you will save lots of logistics cost. That's not all. Combining all these makes your customers happier with your services.
Routing is tough.
Route optimization. Let's say you're a traveling sales rep for Ralphie's Robots with his brand new product, the Pocket Picture Printer. Ralphie gives you a very specific mission. Leave the robot warehouse, visit 2 customers, and return having traveled the shortest distance possible. He thinks he can fool you, but you know stuff. The solution here is obvious. You leave the warehouse, walk to your first customer, followed by your second, and then back to the warehouse. It's too easy. The distance would be the same, even if you traveled the whole route backward. Ralphie sees your pocket-printed picture proof of delivery and decides you can handle 4 customers. This route will take some pen and paper planning. You can go to customer 1, then 2, then 3, and 4. Or you could go to customer 1, then 3, then 4, then 2. Or you could go to your first, last, and your third, and your second middle, but then you put the... Stop! It takes some time, but eventually you choose your favorite of 24 paths available. Your route is okay, but you arrived late to your last customer. Next week, Ralphie releases the carpet cleaner / margarita maker, and not the other way around, and orders fly through the roof. He sees that your stamina is low and gives you permission to use Ralphie's Roadster Cargo Bot. That should make life easier, right? Well, yes, in part, but now you have to navigate winding roads, obey speed limits, sit in traffic and construction, avoid falling debris, and stop at ostrich crossings. On top of that, Ralphie gives you 6 customers, which gives you a whopping 120 paths to choose from. The customers clamor for more. Ralphie invents a washing machine that files your taxes. Now you have to fit pocket printers, carpet cleaning, margarita makers, and washing machines into the cargo bot to make 10 deliveries with more than 350,000 paths to choose from. Pen and paper planning is worthless as the customers become more demanding. Your whole route has to change because Kevin can only be visited on Tuesdays at 3 a.m. while his wife's asleep because she thinks margaritas are for wimps. Ralphie puts you in charge of 10 drivers with 10 vans driving 10 routes. He invents the winter window warmer, which can only be delivered by drivers who have the skills to install it. Each zone has 21 customers. Planning becomes impossible. You now have to choose the best path out of 2 quintillion, 432 quadrillion, 902 trillion, 8 billion, 176 million, 640,000 options per driver.
So that the fuel efficiency and the time is minimized. So so in general, we can think of m number of vehicles, and there are multiple roads, intersections. They have to offload their items, so they will start from some place where they get loaded, and then they need to offload their items at some terminal state. And let's say the road is such that they should not kind of not just the road, but like they should optimize in a way that they should not kind of both go towards the same destination, because it will be a waste of time. Because let's say a truck is supposed to offload some items, then one truck is enough to offload the item at one destination. So it should not be that they both arrive there, and it will be a waste because only one truck was enough to go there. So why should you send both there? And then the second truck has to again reroute and go to some other destinations for offloading. So these are the things we should take into mind. So let us look into this. So consider m vehicles that move along the arcs of a given graph. Some of the nodes of the graph include a task to be performed by the vehicles, and each task will be performed only once, immediately after some vehicle reaches the corresponding node for the first time. Okay, so we assume a horizon that is large enough to allow every task to be performed, and the problem is to find a route for each vehicle so that the tasks are collectively performed by the vehicles in a minimum number of moves. So overall total number of moves by both the vehicles should be minimized. That's your overall cost. So to express this objective, we assume that for each move by a vehicle, there is a cost of 1 unit. So each move will be 1 unit of cost. So these costs are summed up to the point where all the task has been performed. So we understand this routing problem. So obviously this routing problem, when you play out this on a large scale, at countrywide scale, with large networks and so on, obviously this becomes a complicated problem, and that's why you see so many startups just focused on this routing problem. So for large M, it's a complicated graph, it's a non-trivial problem, and it can be approached by DP like any deterministic optimization problem. It's a finite horizon problem, again, because it's kind of it's a routing problem, so they will start from some place and there is finite length of the road, so they will end somewhere. So can view state at a given stage as m tuple of the current position of the vehicles together with the list of pending tasks. So these are the things. So anyway, like we'll see the example there. So it's an exponential. Overall, the states could be enormous, exponential, because for m it's like they can go through so many possibilities, right? So they can go through so many directions. So that way, it's kind of exponential. So overall, what we want to say here is that routing problem is complex, and we are going to use some suboptimal or the approximate DP problem. Now, this is the two vehicle example where we have a vehicle 1 and then we have vehicle 2, and they are supposed to reach the goal here, which is here, and then the goal another goal is this at position number 7, and then and at position number 9. So, and as you can see, the position of this vehicle, so the vehicle 1 is at location 1 and vehicle 2 is at location 2. Now, how we will approach this problem? So basically, they are supposed to reach their destinations in a minimum number of moves. Okay, so and they go one step at a time, obviously. So what are the ways we can start? So if both of them have some base heuristics. So let us say some base heuristic is there, which means that move each vehicle one step at a time towards its nearest pending task until all tasks are confirmed. So this is your heuristic, base heuristic. Okay, so the base heuristic is given here, and this says that so we are assuming a fully observable case. Okay, so that's important to notice here. We have developed POM-DP framework before, which means that we have partial informations, partial state visibility, and so on. But here we see that all of them it is fully visible in the sense that they know where the goal is, basically. Okay, so base heuristic, when they estimate, they know what is the nearest path to go. So in this case, the base heuristic, if both the vehicles apply the base heuristic, then the nearest goal for both of them seems to be like going to 7. Okay, so in this case, because if this vehicle is thinking on its own and this vehicle is thinking on its own, then for individually for both of them, it seems like in 2 steps they will reach the goal 7, and this vehicle also in 2 steps will reach the goal 7. Okay, so this is the base policy, and the problem with the base policy will be that in the first step itself, both will reach 4. So there will be a kind of a collision there. So the base policy itself has some issues here. Okay, so the whole idea is to improve on that by doing further rollouts. So this is our vehicle routing problem. We both should go to 7 and 9 as fast as possible. So when we do a rollout, then one possibility is like when what we know from rollout is that in a rollout they explore basically. Okay, so the greedy would be let us say going to this route, but vehicle 2 will now do a rollout. So meaning it will explore other than the greedy. So other than the greedy for the vehicle 2 could be this. Let us say, yeah. So this is one possibility. Let's say, and vehicle 1 might explore this. Okay. So what are the possibilities right now after the rollout? So basically vehicle 2, vehicle 1 went to 3. So initial one is 1, 2. So vehicle 1 at 1 and vehicle 2 at 2. Then during rollout, vehicle 2 goes to 5 and vehicle 1 goes to 3. So 3, 5. Right. So this is the rollout done by both. Now after doing the rollout, they will execute the let us say the base heuristic. So base heuristic would mean that. So let me kind of remove this. So this is the state right now. So vehicle 2 is here and vehicle 1 is here. Now the base heuristic will apply here. So base heuristic means from here go to the nearest goal. So from here, if the vehicle 2 calculates its nearest path from location 5, then it sees that that this 1, 2, 3 seems to be the nearest. Okay, and then if the vehicle 2 calculates the other route, then is that nearest? So let us see the other route possibility is 1, 2, 3, 4, 5. So this cost is 5 and this cost is 1, 2, 3. Another possibility for the vehicle 2 could be let us say, okay, so here it's like 1, 2, 3, 4. Okay. So what vehicle 2 has done while being at 5 is that it calculated the shortest path, and according to the shortest path, this seems to be the good one. Okay, so because that gives it's the least cost. So this means that the vehicle 2 will now move towards 2. Okay, the location 2. So this means that for vehicle 2, kind of this is fixed now. So for vehicle 2, so for vehicle 2, and this 2 is fixed. Like vehicle 2 has done its own calculation, and it will certainly go to 2, because from its greedy policy, after doing this one step look ahead, which was this thing, it went to 5, and then from 5 onwards it did the heuristic, and then from the heuristic it found that going to 2 is better. So for 2 we are done. Now let us look at vehicle 1. At vehicle 1 is at 3 now. So at 3 the vehicle 1 will calculate its cost, total cost now to go to any of these 2 goals. So now if the vehicle 1 is looking at its cost, then what it sees is that it will do the calculation for which of these is nearest. So it sees 1, 2. So this cost is 2 for vehicle 1, and then it will do it has other possibilities to explore as well. It may go back also. So another possibility could be is that it 1, 2, 3. So this cost is 3. And another possibility for vehicle 2, which is obviously not a good policy, is that let's say vehicle 1 goes more than here, right? So it can go to this goal as well. So here it's like 1, 2, 3, 4, 5. Okay. So for vehicle 1, it is clearly going to 6 is a good idea. Okay, because that's how it has a, according to overall cost, that's where it's the minimum cost. So 6 and 2 is kind of finalized, and then from while remaining at 6 and 2, then they will explore. Then they will do further one step look ahead and minimize the cost overall. So both are at 6. So one is at 6 and another one is at 2. Okay, so this is our current status. So let us use this graph now. So 6 and 2. So vehicle 2 is here and this is here. right? Now they will do the further, we repeat this process. So then they will go for one step look ahead and so on. So and then they will see which one gives them the least cost. So from there again they will see which one gives them this. So they will take this so it already explored this before. So it will now look into this, and it will now look into this, and with this it already arrives at the goal that it's looking for, and in the next step this vehicle 2 will arrive here. So this vehicle 2 is here while this is already here. Okay, so this will be the thing, and then they will explore more. So in this one step it will already reach here. So that's like already it's done. While this might explore a few other things. So maybe it will pick this, looking at the least distance, which is going from here to here rather than going from here to here. Of course, this guy going for this doesn't make sense now because this is already taken. But since this guy has one additional move left, it will start proceeding in this way. Okay, and whereas this is done, it will later discover that this is like already taken. But as far as rewards is concerned, we will look at when these two goals are achieved. Okay, so that way kind of in those many moves we will say that this is done. Okay, so what we see overall cost, it will be like this vehicle went here 1 2 3 4. Okay, so 4 will be the total cost because that's determined by the longest path. So vehicle 2 kind of arrived late, but only when it arrived, so the whole thing was over. So 1 2 3. So this cost 3, but we will take the one like that is the maximum, I guess, right? Okay, so this is what is described here. So this is how these rollouts work. You can encode this nicely. So all this is explained here, so I will skip all this. Okay, so let us look into some of the issues that we may face when we apply these heuristics when we do rollouts. So for that we will define something called sequentially consistent. So we say that the base heuristic is sequentially consistent if it has the property that when it generates the sequence xk to xn starting from state xk, then it also generates the sequence xk plus 1 uk plus 1 to xn starting from the state xk plus 1. Okay, so do you understand this? This looks like very, it may sound like a very trivial thing, but what it says is that there is a sequential consistency should be maintained. If in case your policy from k generates xk plus 1, xk plus 2 and so on, then if in case you arrive at xk plus 1, then from there onwards it should produce the same sequence that it generated from xk onwards. So there should not be change in your behavior in the base policy when you arrive at a future location. Okay, so this is what it means by sequential consistency. Okay, your base heuristic should be consistent with this. If it is not, then you will get into all kind of troubles with the cost calculation and so on. Okay, because your base heuristic behavior changes from location to location. Okay, so we will see some of the examples here. So I hope you understand what is sequential consistency. Sequential consistency means that your base heuristic is kind of deterministic in its or it's kind of unique when it's once a base policy generates a trajectory, then regardless of where it starts, the remaining trajectory will still follow the trajectory that was the one you got starting from k onwards, and the trajectory that generates from xk plus 1 will be same for that time duration. So I hope this is clear now. So basically in words, base heuristic is sequentially consistent if it stays on course. Okay, it stays the course. Okay, so as an exercise you can try for a traveling salesman problem or the multi-vehicle routing is a sequentially consistent. So the base heuristics used is sequentially consistent. Okay, in the traveling salesman problem that we have seen a long time ago.
The original problem involves a traveling salesman who needs to visit several different cities. The question is which order to visit the cities to make the shortest possible trip, in which the salesman visits each of the cities once, and then returns to the original position. Usually subtours, where the route is broken into multiple trips, are not allowed. What makes this seemingly simple optimization problem interesting is that it applies to a lot of other interesting problems with real-world impacts. For example, a package delivery company might want to plan the shortest route to deliver the day's packages to save time and fuel. A school district has similar concerns when planning the best route for school buses to take children to and from school. When manufacturing circuit boards, picking the best order to drill holes can increase the efficiency of the process dramatically. In drone flight planning, choosing the optimal path through the desired waypoints can reduce time or extend the area that can be covered in a single flight.
And in the multi-vehicle routing that we just saw, they are sequentially consistent. Okay, so you can try proving this. We will put this in the assignment again. Now, what could be a not sequentially consistent? Right. So we define sequentially consistent. Then naturally, like what could be not consistent problem? Like, are there problems where like where the policy changes over time? So it could be. It depends on the policy. So, for example, let us say the goal of this problem is that you need to go from start to the end. So, let us say your starting position is this, and your end position is this, and your initial policy is, let's say, Manhattan distance. Okay, so initial policy, or let us say your base policy is Manhattan distance. Manhattan distance is the one norm. I guess you are familiar with this. One norm is called Manhattan distance, and why it's named Manhattan, because basically you can think of these as streets in Manhattan, which are pretty rectangular kind of road networks you can think of. So then the taxi kind of goes vertically or horizontally, obviously. Okay, so that's why we call it Manhattan distance, or sometimes taxi cab geometry. So, but you should be in Manhattan for that, I guess, because other places is not really rectangular, right? So like in India, we don't have rectangular grids. Like there are very few cities where we have such planned a grid-like structure, rectangular. Okay, so what do we mean by violating the sequential consistency? So basically it means that your base policy was to follow Manhattan distance, and then let us say you arrive here and here, let us say, and then you said, no, let me do the shortcut, like some motorcycles do, shortcuts on the roads. You know, if there is a gap somewhere, they do like this, especially the motorcycles. So they go like this. So that's violation of their policy. So this is what we mean by an inconsistency in your policy, that you are supposed to follow the road, but then you decided something else. On some other day, you are following the road rules, but on some other day you are deviating away from your base policy. So this is what is called violation of the because if you do that, then how will you estimate the cost and so on, right? So that's the difficulty. So in this case, let us say if we go by the base policy, then this could be one possibility of a base policy, but then it will be inconsistent when you take the diagonal route. So let us say in this case, if you do take the diagonal route, if you are here, let's say xk, and then so let us say this is xk, your current state, and here according to base policy you will take this route, which has cost 2 from xk to arrive at xk plus 1, whereas if you change your base policy at k, then you are in a different, like your cost estimates and all these are different now. So this became your base policy. So going diagonally at state k, you generated a state which or the control that you took is different from the controls that you will take at the base policy. Okay, and this you did when you arrived at xk. Okay, so this change of your policy was done at xk, whereas let us say if you would have started at, let's say, xk minus 1, let us say, so just to to be very precise in what we are trying to say here, if you have started from xk minus 1, you followed Manhattan trajectory until the end. Whereas if you are at xk, then whereas if you are at xk, then you went diagonal, and maybe you kept going diagonal, or maybe you went through Manhattan distance. So there is an inconsistency in your policy. That's what, and we are only talking about the base policy right now. So base policy is something we want it to be unique, regardless of where we start from. It generates the same unique remaining trajectory. Okay, it does not change given it goes to a new state. So that's what it means by sequentially consistent. Okay, so so what about cost improvement? Okay, so we call a rollout policy, let's say, so consider a rollout policy pi tilde with sequentially consistent base heuristic, and let jk pi tilde denote the cost and so on. Then in that case, this is kind of guarantee, because if I have a sequentially consistent base heuristic, then if I use a rollout policy, then it will improve or remain as good as heuristics. Okay, so or as good as the base policy. So this doesn't get violated in those cases. So you will do the rollout, you are safe to do the rollout because your base policy is consistent. So you will either improve or you remain like base policy. So you will not increase or you will at worst you will be worse, at most like a base policy. Okay, so so in that case, we will call, we say the base heuristic is sequentially improving if for all x, k, and k, the q factors that we have, or the q factors corresponding to the rollout, it is like less than or equal to the heuristic. Okay, so all this. Okay, so if it is sequentially improving, then you will do this cost improvement and so on. So this is already like written as a theorem. You can write this as an exercise. You can see the book. Okay. So as we said, so we have a trajectory T0, which is the base, the trajectory created by the base heuristic, and let us say Tn denote the final trajectory via rollout. So we did a couple of rollouts, and then we arrived at these, and then there could be some intermediate trajectories. So then what we can also show in general is that these rollouts keep improving sequentially. Each time they keep improving the cost of the trajectory. By improving, we mean the cost keeps decreasing, because the whole point of this rollout is like we change the policy when we see an improvement, otherwise we don't. So this is why we have less than or equal. So in the worst case, we will not change our trajectory, and whenever we see cost improvement, we will change our trajectory. So that's kind of trivial. Okay, so when the sequential improvement gets violated, so sequential improvement will get violated when we don't have sequentially consistent base heuristic. So this is one of the illustrations where you see that. So this is the optimal trajectory chosen by base heuristic at x0. So if the base heuristic starts at x0, then it follows the trajectory x1, x2. Okay, so basically the x0 goes to x1 star, goes to x2 star if it starts from x0. So this is the trajectory chosen by the base heuristic. But then if it does a rollout, then rollout choices are like these is one possible rollout choice, but this is also one possible rollout choice. Let us say after reaching here, then it may do another rollouts. So so these are the possible rollouts at this stage, and these are the possible rollouts at this stage. Okay, so if it does this rollout at this when it arrives here, then the base policy kind of is not consistent, and it goes this way. Okay, so after arriving at x1 star, after the rollout, let's say it might come to x1 star again, or it might go to x1 tilde. So if it comes to x1 star, and from there if it has to apply the base heuristic, then since it is not sequentially consistent, it goes to the other way, which is x2 tilde. Okay, so I hope this makes sense to you. So this change in the heuristic nature of the heuristic happens after you have moved to the future state, and when you apply the heuristic, then kind of it's not consistent, so it goes in other way. Okay, so the base heuristic as a whole generates this trajectory, but when I do a rollout, and in rollout, let us say I arrive at x1 star, and then I apply the base heuristic, then my nature changes and I go to x2 tilde. But if I would have applied the base heuristics x0 onwards, then it would produce x0, x1 star, x2 star. Okay, so this is where things are tricky, where it is not sequentially consistent, and hence the cost improvement is not there, because this was not the optimal route that was supposed to be taken. So this, as it happens that this, because of this changing behavior of sequential inconsistency, you get to some suboptimal route. Okay, so anyhow, this problem can be kind of solved if by so what if sequential improvement does fail? So what are the ways we can do rollout that it is taken care of? Okay, so can we develop an algorithm that still works? So yes, we can do something called fortified rollout. So basically what it means is like you keep the best possible trajectory anyhow, like saved, and then you only change those when it is kind of gives you an improvement. Otherwise, why should you change anyway? So this is what it does here, that let us say up to xk you have this trajectory called permanent trajectory, and then so x0 to up to xk you have something, and then you have like a tentative base trajectory, trajectory. So basically from xk onwards you have uk tilde and up to xn tilde. So this is your tentative tentative base trajectory, looking at the minimum of these cost basically, and then the update rule is if the cost of end-to-end trajectory tk tilde is lower than the cost of tk. So if the cost of end-to-end, meaning from starting to the end, if the total cost is lower than the cost of the current trajectory tk, then only this control uk tilde xk plus 1 tilde is added to the permanent trajectory. Otherwise it is not. Okay, so basically the rollout algorithm, if it is done in a way that the policy changes only if you look at end-to-end trajectory, then nothing, no issue can arise. And this is something we have done with some examples before, where, because even if let's say the policy changes along the way, if the total cost remains minimum, that is what we are looking for. Okay, so whatever heuristic policy is there, and we do the look ahead and so on, anyway we keep track of the total cost and only update when it is giving us the minimal, then it should not be a problem. So in the permanent trajectory, in this case, we will add this control because the tk tilde cost is lower than the tk. Okay, so we can also use multiple base heuristics. It's not necessary that you use only one of them. So in problems with multiple base heuristics, we can integrate all heuristics by creating something called super heuristic. So this super heuristic selects the best trajectory produced by the collection of heuristics. So in this case, let us say there are m heuristics, and then the trajectory generated by let's say the lth heuristic is this tk tilde l. So it starts from k plus 1 and so on up to n, and then the super heuristic identifies the trajectory tk tilde with minimum cost at state xk plus 1. So overall, this minimum, since you are given these m base heuristics, so what it says is like based on each of these heuristics, you generate this cost, and then and for all u, and then choose the one which gives you the minimum cost. Okay, so basically you can do this in parallel also, because there are because in this case there are m base heuristics, so let each of these m work in parallel. So just like usual base heuristics that you use, you compute each of these costs using these minimum these base heuristics. So this can be we can do this in parallel, and hence we call it parallel rollout. So overall, if the heuristics are sequentially improving, then same will be true for super heuristics. So this still holds for all L equals to 1 to m. These so earlier we had like q less than equal to h, but now we can say it's the same for all the L individually. Okay. So overall, we can say that this is again sequentially improving. We can take this minima inside, so we can interchange this minima, and then overall this is less than the minimum of all these m q factors cost will be minimum of all the base heuristics basically. Okay, so overall you can see that this kind of even with parallel rollouts, we are supposed to do sequential improvement. So so one other possibility is like doing a simplified rollout. So in simplified rollout, basically we use a subset of the controls. That's all. Okay, so you are given a large set of controls, but then in simplified you just truncate the set of all possible controls. You choose controls only from a small subset. In this case is uk tilde xk. Then we can call it a simplified rollout. Okay, so again we can skip these proof. Why? Yeah. So another variant is something called truncated rollout with terminal cost approximations. So when we do rollout, we go until the terminal state, but what we can do is that we may not go to the terminal state, because the terminal state, like let's say that it's a very large horizon problem, we may stop somewhere in the, with the knowledge that we have some cost calculated midway, okay, midway or like sometime in future, but we don't want to go until the end. So this will be called terminated rollout. So rollout trajectories in this case are obtained by running the base policy from the leaf nodes of the look-ahead tree. The trajectories are truncated after a given number of steps. Okay. Now where you will truncate, and that could be essentially a hyperparameter. Depending on the problem, you will truncate too soon or much later. So
Let us look at
AlphaGo, they do
AlphaGo
this truncated
0.
rollout.
So in the game of Go, there's a branching factor of around, say, 200. And at each one of these positions that you're in, you have 200 possible actions that can be taken, and leading to new positions where, again, there's 200 more decisions that can be made, and so forth. And this actually lasts for several hundred moves. And so we actually have something like 200 to the power of 200 possible sequences in the game tree. And so this really renders the game of Go completely intractable to traditional search methods, and has meant that something new is required to make progress. So at the heart of AlphaGo are two convolutional neural networks that represent knowledge about the game of Go. So the first of these is the policy network, which is illustrated here. So the policy network, which we're denoting by this green P in this talk, represents AlphaGo's recommendations of moves to play. So in each position, it's fed in a representation of the position as different planes representing the board, such as where the black stones are, where the white stones are, where the empty intersections are. And this is fed through many convolutional layers to process this position into increasingly abstract features representing knowledge about the game of Go. And finally, this is brought together into a policy distribution over moves that actually recommends which moves to play. So in this situation, for example, we can see that toolbar is suggesting that in this particular position, one particular move is considered to be a very good move and is suggested and recommended with high probability, whereas many of the other moves, such as playing in the corner, would have near zero probability. And so this is how AlphaGo recommends which moves to play. The second neural network in AlphaGo is called the value network, and this represents AlphaGo's positional evaluation knowledge. And essentially what it does is it predicts the winner of the game. So again, it takes a representation of the position of the game of Go as an input, it processes it through a convolutional network, but this time it kind of takes that and it aggregates all of that knowledge together in a final layer that combines this together into a single scalar value between -1 and +1, where +1 means a prediction of certain win for AlphaGo, and -1 means a prediction of certain loss. So these neural networks are trained in AlphaGo, and I'm going to represent a slightly simplified representation here of the training pipeline in AlphaGo, which is based on a pipeline of classical machine learning approaches. And at the beginning of this pipeline, we start with a human data set, a data set of positions, and for each position we have a label that says what the move was that was chosen by a strong human player. And what we do is we train our policy network, first of all, by supervised learning to classify that human move, to say in this position we would like our network to predict the same move that human played in that particular position. And once we have this policy network P, we're able to play games against itself using the policy network, for now without any search at all. So it plays games against itself, the policy network picking a move for both players, for both black and white, all the way through the game until the end of the game, at which point we have a winner of that game. And what we do is we then train our value network, this value network which we indicate by V here, this pink V, we train the value network by reinforcement learning to predict the winner of the game from each one of those positions. So from every position we would ask our value network to correctly predict which of those two players, black or white, will win when the policy network plays against itself. So that was the original AlphaGo training pipeline. And the main idea of AlphaGo is to really use the policy network and value network to make search tractable. So again, we see here a kind of cartoon representation of this enormous search space that we have in the game of Go, where here we're just looking at a cartoon where we have just 2 different moves that are possible from each of these small states, but in reality there'll be several hundred moves, and this tree would be vast. And so what can we do? How can we make this search tree more tractable using our neural networks? Well, the first idea is to use the policy network to reduce the breadth of the search tree. So recall that the policy network suggests moves to make in each position. And so we can actually reduce the breadth of this search by only considering moves that are recommended by the policy network. So instead of searching 200 or so moves from each state, we might consider just a handful, and just kind of expand that handful of moves in the search tree to dramatically narrow the set of possible sequences that we need to consider. The second idea is to use the value network to actually reduce the depth of the search. So the value network predicts the winner of the game from any position. And so that means that we can actually use the value network to replace any subtree of our search tree with a single number. So that means that we can actually, instead of searching all the way to the end of the game, we can truncate our sequence at a leaf node, and we can replace the subtree that we would have had to search systematically all the way to the end of the game. We can replace that whole search tree with a single evaluation of our neural network.
Then here we see a multi-step look ahead of 5 steps, and rollout truncates at step 5.
And this dramatically reduces the size of the search space that we need to consider. So in practice, we actually use a more sophisticated search algorithm than that cartoon suggested, which is based on Monte Carlo tree search. So I'm just going to briefly illustrate how this works. If you'd like more details, you can read the papers and so forth. But the algorithm proceeds in 3 stages. So in the first stage, the algorithm traverses the tree from root to leaf. Picking at each node, it picks a child based on a kind of upper confidence rule to decide which action it should select. And so this rule actually selects actions that have been evaluated most highly in past simulations. That's this Q value from each node. And it also prefers to choose actions that the policy network likes. That's this U term. The U term kind of is a bonus term that includes what the policy network thinks of the move. In the second stage, once we've actually traversed this simulation down to a leaf node, we expand the leaf node and evaluate this new node with both the policy and the value networks. And finally, in the third stage, we back up the evaluation. So whatever this evaluation was according to the value network, we back that up through the search tree so that at every node we maintain the mean evaluation from each of those edges. So each Q value there is basically storing the mean evaluation that it's seen from that point onwards in the search. And this process of Monte Carlo tree search, can very effectively expand a very large search tree by just considering that the most important parts of that search tree get expanded, and it systematically kind of gets deeper and deeper and deeper, but in a very selective fashion, so it only considers the important parts of the search tree.
You don't want to go till the end because the space becomes so huge. So you do estimate up to, let's say, certain number of steps, like k equals to 100, and until then you compute the cost. So, so this approach is important for large number of stages. Alternatively, the terminal cost function approximation may be done by some offline training process and so on. So we will see some of these when we go out in future. So one possibility is rollout algorithm for discrete deterministic optimization problem for the case where we don't know the cost. What will you do when you don't know the cost and the constraint of the problem? So let's say we don't have the cost available. So how will you do the ranking of the solutions that you get, right? So in this case, so instead, let's say we have access to a base heuristic and also a human or software expert who can rank. So let us say you have some base heuristic, but still you don't know kind of a way to compute the cost. So let us say you generate something from the base heuristic. Some output comes. Then you do rollout. So you have base policies, you do look ahead and you generate something. Then some other answer comes. So you generate this a lot of answers, let's say. Out of that, maybe there is an expert that looks at. Now this expert may not have themselves a way to give you a cost approximation, but they will say, okay, this looks good. This doesn't look good. So that way, let us say there is an expert that can evaluate somehow the whatever trajectory that you generate. Then also it's okay. It's somehow like we don't have a model in our hand to compute the cost, but we rely on some expert to generate this. So this will be a model-free approach. So basically what expert will do is that the expert can rank any two feasible solutions without even assigning the numerical values. Okay. So for example, when you do generative modeling, then it is very hard to, in general, to determine let us say if you do generative modeling for images, then sometimes it's hard to determine what is the quality of the image generated. Okay, so in images it's quite, so you may want some expert to say that, okay, look, this image that is generated it looks better compared to some other image, okay, based on some parameter that the expert thinks. Okay, so so that way, in some of these problems, you may say, okay, there is some external expert with some intuition, by some way they kind of know how to judge these final outputs. Okay, so in general, we have this discrete optimization problem for selecting the control sequence to minimize this this general optimization problem, and we can assume that each component is constrained to lie in a constraint set. So a base heuristic is given, let's say, and a partial solution is given. It generates for every u in uk. Yeah, so basically it generates this these sequence. Yeah, it also allows for some empty solutions. And let's say the third, this part is like an expert is available that can compare any two feasible solutions, u and en and u2. Like whatever we said is just written down here. Okay, so again, the rollout can be applied and so on. It's the so everything remains kind of same. The only thing is here is that we are now dependent on this expert rather than the cost. That's all to take away from here. So this is what it looks like, the illustration of these. So you have a current partial solution, and then you apply some base heuristic. You are allowed to do look ahead, obviously. So you apply some base policy. So when you do the look ahead, you will do look ahead, and you have base policy go to the terminal. But there will be an expert that will tell you, okay, this is good. And when the expert says that it's good, then you say, okay, my look ahead is a good one. And then you update your base policy. So the whole point is that you don't have a cost in hand. There is an expert who tells you, you generate with the look ahead, but there is a, whatever you can, it may, like only when expert tells you that this is good, it's like the cost estimate. And then you say, okay, this new look ahead direction is good for me. So that's how it works here. So there is, so only thing is like there is an expert here at the end, according to which you will say that now my look ahead step, which is uk plus 1 tilde, is a good one to take. So so that's how this will work. Yeah, so all this remains the same, like we said. Finally you decide based on the expert. Now can we use LLM also, like for rollout? Because the LLM can be seen as an expert, who knows, right? So let us say I'm solving some problem and I don't have any cost estimate in hand, and for that problem I generated a sequence of steps, and then I asked the LLM, is this a good idea? So let's say I'm playing, let's say, hide and seek, and hide and seek, in hide and seek I can have the base policy where I may do something interesting with the let's say I have some base policy where I will just hide in some corner. That could be like some base policy. That may not be the good policy. Wherever there is a corner, I will hide. Right? So that could be the nearest corner. So maybe I will do that, and I will generate a trajectory of this, and then at some point I get caught. So this will be a sequence of trajectory with the terminal state that I got caught this many steps. So then there is an LLM sitting there, and you can describe this trajectory. These are the things I did, and this is how I ended up. Then LLM is an expert for you. They say, no, you could have done something like this. This was not a good thing. The action that you taken at some stage was not a good one, just to hide somewhere, maybe move the block some near the door. So, this LLM is telling you kind of as an expert what to do. So then you updated your policy, and then so it's like you did a sequence of steps, and then at K step you let's say you ran to the corner, and then you saw that you got caught, and you got a very bad you got caught basically, and then you can then tell the LLM that at the K step I did this. Then the LLM can say, no, what about that? So LLM might say that this was your bad thing, or let us say LLM only tells you what is good or what is bad. So that itself helps you to kind of change and explore something else. So you tried something else. Maybe you went towards the block and tried to push it near the door, and then so basically it generates the final trajectory, and you won because after certain time steps the seekers could not find you. So this trajectory, then LLM will say, yeah, this is a good one, and so on. So LLM could be seen as an expert. So the problem of minimizing this over can be seen as an n-gram optimization problem. In example before, we calculate these partial solutions, and a GPT can be used as a policy to generate the next word within the n-gram context. Okay, so basically here words could be seen as like a state, and then the choice of the next word is an action that you are supposed to take. The problem can be tackled using a model-free rollout, where the GPT acts as a base heuristic for completing partial solutions. So at K step, you may use GPT as to even tell you what to do next, maybe. Okay, so main issues with this approach is like how to train a GPT specifically for problem at hand. Now it can be a circular thing. You are learning a policy, you are trying to improve on a problem, but then you are relying on GPT. So apparently the problem you're solving maybe not really, I mean the very reason why you're solving this problem maybe it's because GPT doesn't solve that, maybe. So it could be a chicken and egg problem where you are using GPT to solve a problem, but you're solving the problem because GPT doesn't really solve that optimally, maybe. So how to train a GPT specifically for problem at hand. So and how to handle absence of explicit cost function, because there is no, let's say, a good way to compute reward. So how to design an expert software for comparing let's say a complete solution. So these issues are currently active area of research. How to use LLM, and then also a way to kind of give rewards and so on. Recent developments have gone in these directions with some ideas. For example, if you look into DeepSeek, the way they evaluate the reward, then they introduce something called group relative policy optimization, and this involves like accuracy rewards. So problems with deterministic results, like if it's working on maths and coding problem, then obviously in maths and coding the problem will be given to you, and you have to write down the code. So coding is a very nice problem in the sense that in coding you have to reveal everything. Like coding, you cannot just say the final answer and say it's done. So that way coding is a way to explain also what you did. It's about reasoning. So when you do coding, you train something to do coding. It's as if like you are making it go through all the steps and not just give a answer in the end. So in maths problem also, like in maths problem, sometimes one can kind of give the answer directly. So if I ask an integral of something and then I get the answer, but then sometimes integral involves, let's say, some steps, like let's say you write it integral by parts and then you separate those and so on. So basically you do this in 3-4 lines and then you get to the answer. So this is called kind of the reasoning, where you are kind of explaining the process steps in your answer. Here again, in maths problems, the model must provide the answer in a specific format so that it's reliable. So by a specific format here means it shows me steps of the answer. So basically it gives me the detailed solution and not the final answer. So for coding problems, lead code compiler generates a feedback using predefined test cases. Other could be, so what we saw is like one of the problem is like how to define the rewards. So rewards in these cases, let's say it's a deterministic problem, coding and maths problems, and then we can look at rewards which are based on the correctness. That's the first one of the rewards, that did it give me the answer which is correct. Second is like the specified format. Did it produce the answer in a specified format? By specified format, we may also say that, let's say in the reasoning format, so did it give me answer in one step after the other? So that can be part of the format. And of course the feedback could be given, let us say, by there is a compiler that can run your code and give you for various test cases whether your code works or not. So we know in online coding judge, we have these things where you submit the code and they tell you whether your answer was correct or not. So those could be also seen as kind of reward in the coding, especially format reward. As I said, the format, let us say, is this within some tags? So let us say thinking tag. So if it produced an answer, let us say step by step, so then did it produce something like that? Think, and then some answer was generated, and then let us say some way to close the answer, and then we may have another thinking step, and then we close that thinking step. So this can also be seen as a correct way of formatting, where it tells me that these are the ways I thought, so these are my thought. And then after that, these are my thoughts. So this is the format that we might be looking for, and this is also a part of the reward. Did it do in correct set of process? So so rewards are assigned based on adherence to specific formatting structure. Okay. So in the DeepSeek paper, if you see, they do put this think tags, and in between, or the way it thought about something, it writes that. Okay. So it's not just about the final answer. So for each prompt, the model generates multiple responses. So this is like what we have in let's say rollout. So in rollout, I have a base heuristic. Obviously, that's one possible outcome, and then and then I do a look ahead and roll out, then I produce another outcome, then I do another look ahead and roll out, then I produce another. So basically, when we are training these, then we do generate these multiple responses while we are doing look ahead and roll
Assume
out.
that we want to make a reasoning model for chess. Look at this chess position. We will generate multiple response through LLM.
Response 1 from LM. Response 2 from LLM. Score for response 1 is 0.5. Score for response 2 is minus 0.3. Based on these scores, response 1 is preferred.
In DeepSeek, instead of PPO, GRPO is used. Step 1, generate output SO0, O1. As step 2, give reward through reward model. In chess, using Stockfish step 3, compute group advantage or relative reward.
Then the whole point is that when it's a model based, then I do have a cost. So there is a benchmark that I use to say, look, out of these possible outcomes, this is the best one, and that allows me to update my policy. So here it's like in a very in cases where the model is not there, then we rely on the expert. And then the problems where we are looking for modeling, then and reasoning, training a model to reason correctly. Here we need these multiple ways to look at the rewards. So here the rewards are in multiple forms. What was the final answer? Was the formatting correct? So did it go through some thinking steps one by one, and so on. Right? So each response is evaluated using a predefined rule-based reward, and rewards are calculated as follows. As I said, correct or incorrect answer, and then proper formatting and all. Improper formatting gives you the possible penalty. So what DeepSeek does is that it does get away with a separate value network, in the sense like the cost thing. So what it uses is something called group relative policy optimization. Okay, so this is a very hot paper, like came maybe like slightly more than 10 days ago, I guess, or 2 weeks. So so group relative policy optimization is more about related to the current group policy. Is the current trajectory giving me more than the average reward? So it's a more of a relative way to judge someone. It is more like a relative grading in class. Okay, so in relative grading, we are always looking for a benchmark which is the current best person who has the highest mark, and then the average person who is this. But if the class changes to some other next year, then the base and all this might change. So it is more about group, so that's why they call it group relative policy. So based on the group average policy that we have now, the current trajectory compared to this, was it doing better than or not? It is not looking at the absolute. It is not looking at the 100% marks that one can get as a max. It is not looking at that. It is only looking at the relative average, and based on average, just like relative grading, how better it does. So for each input prompt, model generates multiple candidate outputs, and these responses are scored using a reward model. So in this case, these rewards are there in these reasoning models. These relative rewards are like the final answer. But what we want is that we want to improve on that. Okay, so that's where kind of we have this RL involved here, in the sense that we want to keep improving, just like we do it in a rollout with look ahead steps. So there is a correct answer. There was some thought process, but what if it generated another set of thought process, and did it do better in terms of these formatting rewards and so on? Okay, so the group of responses is evaluated relative to each other and not against absolute standard. Just like I said, there is no absolute reward as such. It's relative to each other. So that way we reinforce, like we train these models as a pure RL thing, that they keep improving on top of each other. So if you want to see, let's say, how it could be done. So let us say this is a maths problem where I will take 2-3 minutes more. So let's say this is a maths problem where, so if John has 5 apples and gives 2 to Sarah, then how many apples does he have left? So this is a maths problem, and we want to build a reasoning model where it will give me a sequence of steps to solve. So response generation could be like this. So response A could be John has 3 apples left, and John has 2 apples left, and then John started with 5 apples and gave 2 away, and 3 apples remain after giving 2 to Sarah. Okay, so these are the possible responses that might be generated. Maybe let's say you have some base LLM model which can generate these solutions in a multiple different ways, and then your whole goal is to rank which of these is a kind of a better response to your reasoning model, and the reasoning model will reinforce its policy so that it learns to give a better answer. So here if you see, then if we look into the reward calculation of this, then reward model evaluates each response. So the correct response is A and B that receive the highest reward. So basically A is like this is A and B cannot be correct simultaneously, right? So John has 3 apples left. This is true because A gave 2 to Sarah, right? And 3 apples remaining after giving to Sarah, right? So D is also correct. Yeah, D should be there. I think this is a mistake here, I guess. So A, John has 3 apples left and 3 apples remaining after giving 2 to Sarah, right? So John has 3 apples remaining, right? Something like that. So out of these possible outcomes that you see, 2 of these are the good. I mean, they do solve the problem, and they have good. So you can give them like good rewards and so on. So then GRPO goes into a slightly more. So it is a RL based method. So basically, let's say you have some discounted rewards and so on. But then what it does is that it defines these so-called relative importance for groups. So basically, this is the old policy, and this is the new policy, and this is the group. Okay. So basically, it looks into this ratio and does this ratio kind of improve based on whatever reward it has compared to the base policy G. Okay, so overall this has this loss function. So I will at some point I will go into more detail of these final loss function and the full DeepSeek, because it does fit very well in our framework, because RL being used to do for reasoning is basically the same. We will get into a bit more detail of these things in practice, like how these GRPO really works. Okay, so let us stop here and we'll continue.